left. I think it was the BCD outer.
I didn't do that yet.
We just finished. I think we were going on the PCD and validation.
Alright. And we're talking about visual object. It's also what you talked about.
We have a customer.
Are you going to the thing tonight?
Yeah.
No, I'm 99% sure she's doing the exact same thing she did on yesterday, but like maybe if I see it twice, I'll know
It'd be
it.
nice to see you again. This one is finished.
All right, let's get started. Welcome to Lecture 21, CSE 53, 23, 73, 23, Mobile Sensing, Learning, and Control. How's everyone today? Everyone seems very happy to be here, which is good. That's great. That's wonderful. I like sarcasm. Okay, so course logistics. Yeah, A4 grades are coming, I promise. A6 is due next Thursday. Just a reminder to show me a working demo this coming Wednesday, not today, but a week from today, or upload a video for that. The final project proposal is also due this coming Thursday, right? And I'm hoping that that will be a nice ramping so that everything gets ready and you're all ready to go for the final weeks of the class. Okay, any questions on final project proposal that I haven't gone over, or that I have gone over and is unclear? Last chance. Okay, good. Let's move on. Okay, so the agenda for today is to finish off. We got through all of the intuition and theory that I wanted to get through on machine learning, kind of. Today I want to talk about the pitfalls of machine learning, and then we'll get into NumPy, SciPy, and Scikit-Learn. And then we'll go over the assignment 6 code base that I'm going to give you guys. I don't have a video today of me because I've updated my laptop, and for some reason that doesn't work. And I just found out 10 minutes ago, so I haven't fixed it. I'm sure you'll be fine. No one cares, especially you guys. Okay, big data pitfalls. Last time we talked about how machine learning was going to save the world, essentially. And I gave you a bunch of examples of how it could save the world. And you guys were really excited about it, and that was good. Nothing. Wow, what's going on? What's up? Okay, guys are doing okay? Everything's fine? Essentially what we talked about last time were decision trees, random forests, k-nearest neighbors, support vector machines. We ended the lecture with a little demo of support vector machines and how essentially the support vectors get made and how the different max margin classes get made, right? It's pretty good? Yeah. What's KNN? Somebody tell me what KNN is. Yes. How does it work?
Depending on how many neighbors you look at, if it's, you probably classify something. If there's more of one type of class close to it, it's going to classify as that.
Yeah. Essentially, you take the majority class, right? Or the plurality class, whichever you have the most of. You guys know what the difference between plurality and majority is? Yes? No? A majority would be like anything over 50%. Right? A plurality is just the maximum percentage. That make sense? So 33% is bigger than a bunch of 25s and 17%. So the plurality, even though it's not a majority, it's the max. It's like any political system except that in the United States. You know what I mean? No? Yes? I'm going to assume yes. We're just going to keep moving on. Okay. Essentially what I want to go over today is that there is no free lunch. Have you guys ever heard this before? What does it mean? It means that nothing is free. That is true. That's absolutely true. This actually comes from a seminal paper in machine learning where they talk about there's no free lunch. Essentially, what they're trying to talk about here is that randomness, if you don't know something about your problem, you will never solve anything about your problem. Right? And the example that they gave, the kind of quintessential example they gave was, okay, let's say you go to a restaurant every single day, all right? And you go to a random restaurant every single day, and the menu items are exactly the same in all of the different places, but the prices of each item shuffles, and it's just randomly shuffled depending on where you go, right? So if you know nothing beforehand about where you're going to eat lunch or who's offering a deal, right? You are randomly, awesome. You are randomly going to go in, and your meal is going to cost what? You have no idea. But on average, everybody's going to pay about the same price, right? If the menu items are completely random and you go to a bunch of random places, on average, everyone will pay about the same amount, right? There's no way to game the system, all right? There's no free lunch, okay? But let's say that you have a friend and that friend is vegan and they go to lunch with you every day. They may, because they're constraints, they're not choosing now at random from the menu. They're choosing specific parts of the menu. They may actually pay more or less than you because they've constrained the problem. Weird. That was, anywhere. That's where no free lunch comes from. Is that okay? You don't have to exactly understand it, but now you know there's no free lunch. Okay? Unless you get, I don't know, Groupons. And then there might be a free lunch. Okay, good. At least somebody's smiling. Okay, let's talk about pitfalls in big data. This will be fun. This will be really good. We'll take 20 minutes and do this. Okay, so we talked about machine learning. Machine learning can detect correlations, right? That's all it can do. Correlation is not necessarily causal, right? So a really good example of that to make you concrete is, have you ever seen the correlation between murder rate and Internet Explorer? Yeah? This is what it looks like right down here. This is the number of murders in the United States graphed on top of the Internet Explorer market share. Okay? Those are highly correlated to one another, but they have nothing to do with one another. From a logical standpoint, they have nothing to do with one another, right? I can show a correlation exists. I can also show a correlation exists between the number of cases of autism and how much organic food was bought in the United States. But there is no causal relationship. The only thing that shows is they were both increasing at the same time. Why? Because organic food was becoming cheaper and
People are going.
well, yeah, you could look at the percentage of people with autism was going up, right? The actual the diagnostics for care of autism became a lot clearer at the same time, and so you had more autism cases show up because it was much clearer. People that were getting misdiagnosed were all of a sudden correctly diagnosed with autism, right? You can show the same thing happened with vaccines, right? Organic food, vaccines, they really have no effect on autism right now, right? Same thing with Internet Explorer and the murder rate. Okay, so no matter how much correlation you can show between some variable and something else, the only thing that machine learning does is learn that correlation. It doesn't tell you anything about causality, right? So something could change in the system, and all of a sudden your learning system is broken. Okay? So machine learning does not learn creativity, right? What do I mean by that? You're not going to solve something really, 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 really complicated with machine learning. And the classic example of this is animal camouflage. Let's say you wanted to teach a machine learning algorithm to how to detect animals that were camouflaged in their natural environment. Okay? If you train up something, let's say you give it a bunch of, and you just give it a bunch of images that are examples, right? Where it's like, okay, here is an animal's natural habitat, and here is the patterns that are on an animal, okay? And you try to have a machine learning algorithm learn what makes a good camouflage for an animal, right? It turns out that's a really difficult problem to try and teach a machine, and it doesn't do very well, right? It will come back with, oh, you want black and white stripes in the desert, okay? But if you have a human sit down with a notepad and try and figure out animal camouflage, well, they'll probably come up with a really good set of rules in a week. Okay? And that's what they did. Okay? Machine learning is not creative. And it can't find really, really deep problems that essentially you need creative thought to be able to understand. That make sense? machine learning can still be very, very easy to game, right? And what I mean by that are, let's say, Google hits. If you want your website to show up higher on Google, Google's a really advanced system, right, that it uses as a search engine. You can still game the system and find ways to get your website to have more hits than anybody else. Yeah? Or has anybody ever used the Microsoft Word, their writing score? Yeah, where you essentially, you can go in and you say, hey, am I a good writer? Right? And Microsoft Word, in all of its wisdom, it goes in, it looks at your document, and it gives you a score for how good your writing is. Are you kidding me? And your reading level. And your reading level.
Like fourth grader.
Yeah. So, right? And wow, everybody goes in there and you can look at it, but you can game that system. The only thing you have to do is write really big words and run-on sentences. And you can score really, really highly. All right? Because it turns out that if you look at good people's writing, one of the things you can pull out of that is that they're very long sentences, right? Which usually have some thought behind them, right? And they use words that essentially the verbiage that they have is they use longer words. Question.
Also works for freshman English.
It also works for freshman English. What do you mean by that?
That's what I did. I did fine.
That is one example, all right? If everybody starts showing up with that, then we'll have an algorithm for it. We'll have an auto-generate paper. Okay? Yeah, it's actually funny. I read a paper, and at the very last part of the paper, what they were essentially talking about was how you can use crowdsourcing and machine learning to figure out how to make your writing better. And so the way that they did that, the way that they wanted to prove a lot of this, the very last section of the paper that they wrote, they crowdsourced. And they submitted it for review. And it was beautiful. It was absolutely one of the best pieces of text I've ever written at the very bottom of the paper. Anyway, that's just an aside. So there are things. But the difference between that is they had actual people in the loop, right? And a machine learning algorithm. The second thing that I would say is results are less robust than you think. So we talked about the stock market last time. What was the problem with the stock market? You guys remember? Yeah?
Everybody follows the algorithm and takes the advice, then it completely changes the stock market and you have to do it again.
Yeah, so if you create a model that changes the stock market, there's a lot of incentive for people to take that model and use it. And the second that they start using it, the model is changed.
One of the constraints for portfolio theory, which is like the information theory behind stock market modeling, is that you do not affect the stock market. Like that's the prime thing you have to consider, is that anything you do won't affect the system itself.
Ooh, yes.
So if you're doing the same thing that everyone else is doing, and that's like a known thing, then everyone's doing the same thing, you might as well be doing it.
Yes.
And then you will affect the system in that sense.
Yes. Wait. I'm not following.
Then you'll be like one giant person. If everyone's using the exact same algorithm, it's like one person using the algorithm.
Okay. Yes. I agree.
That was the point.
That was the point. We also talked about Google's The Flu Tracker, right? Do you guys remember talking about this? Right? What was Google's Flu Tracker?
Based off the search queries to determine what symptoms they have.
Yeah, it looked at people Googling symptoms for the flu, right? And it was able to predict better than the CDC when a flu outbreak was occurring. One time. One time it predicted better than the CDC. The remaining 3 years, it did a lot worse. False positives everywhere. Okay? So the kind of key concept here is that when your incoming data is changing, especially when it's something like the web, your model has to be very, very dynamic, or else it's going to very, very quickly forget what it's learned, because all it's doing is exploiting correlations, right? So if you're sampling from the web and you learn something, that changes on a week-to-week basis, what you've learned and how robust it is. Ah, the Skynet problem. Here we go. So big data from big data. Reinforcement. You guys know what Wikipedia is? Okay, good.
The most useful tool ever.
It's the most useful tool ever. Do you guys know what Google Translate is?
The least useful tool.
What?
Such a lie.
It will actually translate websites directly for you.
Google Translate will translate websites for you. Yes, it will. Does anybody know how Google Translate is trained? Through Wikipedia. They take Wikipedia articles, part of the training. They take Wikipedia articles, and then they take the translated versions of those, and they train the system to go from one to the other. All right? So that's really, really cool. Until Google Translate starts getting used by Wikipedia users. So Wikipedia users like, oh my gosh, we need to translate this into Japanese, right? So they take the English version and they translated it into Japanese. And then Google Translate comes along and it's like, oh sweet, there's a new thing. Let me just train myself on what I just did.
You're saying that both Wikipedia and Google Translate are inbreds.
No, I'm saying that Google Translate is inbred, not Wikipedia. Although if you're reading it in that culture, you're going to look at that and you're like, quoi? And so that's the reinforcement problem, right? Like anything that it learned that was incorrect when it switched over, it just reinforced itself, okay? And it's one of the things, this is really, really hard to catch, okay? But it's something to watch out for, especially when you're trying to pull data from the web. Bogus correlation. This is my favorite one. So if you run 1,000 experiments and you're trying to look for a correlation between, I don't know, two different variables, all right? 999 times, you may get a correlation of almost 0 between these two variables. And one time, you might get a correlation that's like 0.7. Just by chance, by just randomly sampling from some data. You'll get a correlation of 0.7. Right.
Vaccine autism.
So this is one of the cases that happened with the vaccine and autism, right? And it's also the reason that a lot of studies get published, right? People find these correlations, they're like, oh my gosh, look at this. And if they had repeated that study 3 more times, it never would have shown up, right? But the one time that they did it, they get a correlation and people look at it and they're like, oh my gosh. That kind of thing gets published a lot, right? And then the papers that finally disprove it, they get a lot of citations. Okay? Is this clear? Is that okay? Scientific answers to hopelessly imprecise questions. Okay? What do I mean by that? What is the answer to life and everything? What's the quote? What's the answer to life, happiness, and the meaning of
The universe and everything.
the universe and everything? The answer is 42, right? That's what a computer comes back with. Why? Because that's a very ill-posed question. Another very ill-posed question is one of the big data conferences, they decided that they were going to look at big data and see if they could come up with the cultural contribution, the historical contribution of every single person that ever lived. Right? So you go on, and it did pretty good. You get things like, Abraham Lincoln, right? Like Martin Luther King, those kind of things. They start to show up on there. And then like way down at the bottom, it's just, there are things like Orson Welles, right? Which maybe should be in the top 50. I don't know, right? The problem is, that's a terrible question to ask. Data's never going to solve that for you. It's imprecise. It's subjective. There's never enough data to replace human thought, right? What do I mean by that? Well, one of the popular things that you can do with speech recognition is put together what's called a trigram, right? Does anybody know what a trigram is, or just an n-gram? So essentially, like if you had a sentence, right, that said the quick brown fox jumped over the lazy dog, right? The quick brown would be 3 words. It would take that and it would put that into memory. It said that those 3 words back to back, that happened one time in my database. And it just goes out and it looks on the internet and it puts together all of these different things. And now when you take a machine learning algorithm, you can look back and see how often these 3 words happened in combination with one another and get a better idea of how you put together these different like sentence structures for what someone might say, right? That's really great. That's really wonderful, except we can put a sentence together probably right now that has never been uttered before in history. And that trigram never existed. And that's creative thought. Okay? The span of words that can fit into 3 different values is almost endless. All right? You can never learn it, and it doesn't replace creative thought. And authors do this all the time. You look skeptical. Okay. Another thing is big data is very, very hyped. All right? It's cool, but it's not going to answer everything that they, in quotations, say it will. Okay? So if you were to try and put big data on the map of cultural contributions that happened over history, I would say that antibiotics is probably more important than big data. Another thing, if you see something that says, hey, big data can tell you this, and it seems like magic, it probably is. There's probably something wrong. All right? There is no free lunch. All right. Get that. Great. So we want to avoid some of these pitfalls with machine learning when we're putting stuff together. So the first thing to notice is there are lots of ways to be wrong when you put together a machine learning algorithm. And the first one is not to have enough diversity in your classes. Okay, so what do I mean by that? How about this? Here's a music recommendation that you might get. If you like Britney Spears, you might also like the Report on Pre-War Intelligence. Okay, this is a recommendation that no human would make, but the system does. Why? Why does the system think that because you liked Britney Spears, you're also going?
And pre-war intelligence, because spears are like rudimentary weapon. Nice. I don't know.
Oh, that may be part of it.
People that have clicked a button and say they like it or already own it or whatever have done that for both Britney Spears and
Yeah, like it or not, Britney Spears is pretty popular. Yeah, and a lot of people that have the pre-war intelligence in their library also have Britney Spears in their library. Okay? So when you're going on, let's say you're on Pandora, and you're trying to get some recommendations of some songs, and you're looking out there, well, it turns out 48% of their recommendation come from 83 different artists that are really, really liked by a lot of people. 52% of the other recommendations come from around 7,000 other artists, right? So you get a little bit of diversity in there. And then the remaining 300,000 music artists that exist out there don't get any recommendations on Pandora because nobody knows about them. You don't have enough diversity in your classes, right? Most of your examples come from these 83 artists that a lot of people like, all right? You'll see the same thing happen when it pops up on Amazon. Yeah, Amazon recommendation. This is called the Harry Potter problem. It's the same kind of thing, right? If you liked Java RMI, you might also like programmatic unit testing, design patterns, and Harry Potter Episode 1.
Because everybody loves Harry Potter.
Because there are so many likes of Harry Potter, you're bound to get that correlation with Java RMI.
It's bound to also be correct.
And you're bound to also be correct. Yes, you might also like Harry Potter. Oh, yes, I really do like Harry Potter.
Smart machine learning algorithm.
Okay. Outliers and novelty in your data. Well, it depends on what do you normally want to do with outliers? Do you want to shun them? Depends on your application.
I wanna-
but not necessarily like put them in.
Well, first you want to analyze them and see if they're happening for a specific reason.
Let's say you're looking at eggs. okay? And you get this outlier right there. You got a bunch of brown eggs, and then there's a white egg right there. Well, that's bad news if you're trying to look at color of eggs to establish whether or not they are good or bad, right? It's good news if you're trying to detect novelty, all right? Because it means you can use color really, really quickly to figure out you have an outlier, and that may be important, okay? So if you're looking at human behavior, right, and you look at the behavior of a bunch of different people, like say over, a week, when they go do something, it's like, oh, they went to go see, I don't know, a distant relative 1 month and they came back. You probably don't want to use that when you're predicting where they're going to be, right? Because it's an outlier in their behavior, right? But if you're trying to predict when someone maybe is getting the onset of dementia for Alzheimer's, maybe you do want to look at when someone does something that's out of the ordinary, right? So it just depends on what you want to do. Normally, if you're just trying to learn an overall pattern, you want to discard the outliers because there's enough noise in the data that they break your algorithm, right? It's something that we can't learn because we only have just this one outlier example. We don't have enough examples. More data is better than cleverness. So what do I mean by this? Well, it turns out if you are a big company and you want to spend money on figuring something out for a machine learning algorithm, it's normally, almost always, a better use of your money to go out and get more data than it is to try and iterate on an algorithm. And that's just a sad fact of life, right? However, data alone is never enough, right? You can have all the data in the world, and you're not going to characterize a space. We'll go over that. So collecting the right data is very, very difficult. Performance on training data means almost nothing. Why?
Well, it's training data.
It's training data. Who cares that you learned what you trained something? That you trained something that you know what I'm trying to say. Right? So if you're looking at your performance on your training data, and you're trying to show me that, and you say, look, it's 98%, but it doesn't do this, what am I going to say? It's wrong. I don't know who said that. Yes, that's what I'm going to say. Right? I'm going to say, well, you need to probably train it up here and see how well the algorithm works on, let's say, the last 10% of your data. Right? Train it up on 90%, test it on 10. And repeat that 10 times. What's that called? What's it called? Yeah, what's it called if I take 90% of my data, train a model, test it on 10%, and then repeat that 10 times, right? Randomly drawing, say, another 90% of my data. Does anybody know what that's called? Cross-validation? If you do it 10 times, it's called tenfold cross-validation. Yeah, build 10 different models and test them out on data that they've never seen before. Okay, well, that's what it's called. The last thing is dimensionality can be a curse. What do I mean by dimensionality?
Having a lot of comparing values can be great, but can also be really hard to make correlations.
Usually when we're talking about dimensions in machine learning, we're talking about the number of features that we're using. All right? So if I have something where I'm looking at 100 different variables, then I have 100 dimensional features. I have 100 dimensions, right? And it's usually difficult to learn in higher dimensions, right? Just like we can't visualize 4D. Yeah? Okay, moving on. This is a really wonderful paper that summarizes a lot of these points. Go ahead and take a look at it. It's super easy to read, okay? It's meant for the general public. It's meant for college students, okay? More data. More data is a paradox. So the example that I'm going to give you is characterizing a 2D space of integer features. Okay? let's say you have two features, and you're going to try and predict something. You're going to try and predict whether something is blue or it's red. Okay? Let's say feature 1 can have 6 different values. It's an integer from 0 to 5. And we're going to say feature 2 can have 4 different values. Okay? What does my feature space look like? How many different possibilities of features do I have?
20.
24. 4 times 6. Is everybody okay with that? First feature can have 4 values. Second feature can have 6 values. Multiply them together. In combination, there's 24 values that you can have. Okay, so let's say we have 18 examples, right? So up here we can see the blue examples that kind of do this. And then here's red examples that happen over here. Okay, so based on this data, now when we have new data comes in, we have to develop an algorithm which will predict those 6 unknown values in our space that we don't have. But we just didn't have examples right there. Okay? So we have to come up with an algorithm that's going to choose those two. Okay, now let's do something a little more realistic. Let's say we have 50 variables, right? And they're not even integer, they're binary variables. They can be 0 or they could be 1. Okay, but there's 50 of them. Okay, how big is my feature space now? It's 2 to the 50th. Right? So I have 2 to the 50th possibilities in my input space. So there's 1.1 times 10 to the 15th possibilities instead of 24 possibilities. Okay? Right? So that's okay. So let's say I have 1 million examples from the world. I still have 1.1 times 10 to the 15th possibilities that I don't know. Why? Because 1.1 times 10 to the 15th minus 10 to the 6th is still 1.1 times 10 to the 15th. Okay? I can have 5 million examples, and I'm not going to make a dent into that number. All right? What does that mean? That means that you can never, ever, ever collect enough data. Ever. Right? Does it?
Well, your number of variables is that big that you had like 3 binary, you could easily collect any samples.
Yes, you could. So if you have 3 binary features, you're good to go. Let's say we have the iris data set. How many examples are there?
150.
There's what?
150.
There's 150 examples. And what's my feature space look like? There's four features, and they're continuous valued variables. I have an infinite amount of things that could be in there, right? But it's a paradox. Didn't I say this was a paradox? You're right, by the way. So let's say this. Usually, in the real world, data does not span the entire space of your features, right? Yeah, you've got 1.1 times 10 to the 15th different possibilities, but there's usually a lot of structure that you can exploit. And what do I mean by that? Well, if you had to guess, what do you think that class would be right there between the red and the blue? That one? It'd be red, most likely, right? Even though we don't have an example there, it's kind of clustered around the red, right? What about this one? Would it be red?
Yeah.
Probably red, but we're a little bit more unsure, right? We're less sure about that one than we are about the one on the right. Is that okay? So if we want to be more sure about that one right there, what do? You collect more data. You can collect some more data. So more data does help when it gives you examples that show the structure of the problem, especially around places where it's really hard to predict. Right? So yeah, if someone tells you you're never going to be able to collect enough data, that's true. But you can still collect more data, and it's still going to help as long as you collect the right data. You get more examples where it's tough to classify. Is that okay? Okay. Dimensionality. The first thing to know about dimensionality is that, so we're talking about when you have a lot of different features, dimensions, right? Intuition breaks when you're in high dimensions. So here's an example using K and N. You guys remember K and N, right? Yeah? Yes? You weren't here. All right, yeah, so we have this unknown star feature and we want to figure out who it belongs to, right? So we're going to use K and N. Okay, let's say we have 100 different features and we're going to use K and N to solve that, right? So we're going to take distance between the different objects in 100-dimensional space. Okay, you can do it. It's fine. It's just the square root of the sum of the squares. Okay? So let's say that 3 features are important and the rest are just have nothing to do with the prediction problem. In that case, the 97 other features that are in your data set completely mask the 3 important ones. Right? So every time you take a distance and add it up together, it's completely lost. Right? It's like predicting noise. You can't do anything and nothing gets learned. All right? Another problem, that even if all of your 100 features are relevant and something that you need to use, the distances look really, really similar in high-dimensional space. And what do I mean by that? Well, let's say you take a grid of points, okay? And let's say it's in 2D space, and you've got a grid of points, and I pick one of these points, all right? How many neighbors does that point have in 2D space if it's on a grid? It's tough to visualize. I should have drawn it. How many nearest neighbors? How many neighbors that are right next to it? 8. There are 8. There are 8 nearest neighbors. Okay. Now let's go to a third dimension. Okay? And now picture those in a grid. Now how many nearest neighbors does it have? This is kind of cube around. It depends. I should have visualized this because it depends on how I lay out the grid. It's between 16 and 24, right? Essentially, I've got all the points that are on the cube surrounding it. You know what I mean? Okay. How about in 4 dimensions? A lot. You can't visualize it, right? A lot of nearest neighbors. 5 dimensions, 6 dimensions. All of a sudden, all of the distances that you're taking, they start to look really, really similar when you get to higher and higher and higher dimensional space. So even though intuitively you would think that the distance would give you something, it starts to become less important when you have a lot of features. Okay? Another example, in high dimensions, most of the volume of an object is in its shell. Right? So what do I mean by that? Let's say you have an orange. If I have an orange and it's in 3D space, right? This is what I'm used to. Where is most of the volume of my orange? Where's the density? It's in the orange. Is it in the pulp or is it in the skin? What?
Where's the density?
The density.
In the shell.
The density is in the shell. Where's the weight?
In the middle part.
In the pulp. It's in the pulp. The weight is in the pulp. You're right. I shouldn't have said density. Okay. If we take that up to 6 dimensions and you draw a shape right there and fill it in 6-dimensional space, well, or higher than that, you go to 20-dimensional space, and you look at where the weight is, it's in the shell, not in the inner part of the shape. Right? That is really, really, it makes my brain hurt, okay? It's really hard to visualize that, right? But it's one of those artifacts of working in higher dimensional space. Okay? So we need to find a way to ease the learning process. Let's say you've got 100 variables and you want to use all 100 variables. What can you do?
Can you separate them out and analyze like 3 at a time or something?
You could separate them out and look at 3 at a time. You could reduce the dimensionality some way, right? You look at just a few of them at a time, right? There's lots of ways that you can reduce dimensionality. Does anybody know any of those TLAs? Principal components analysis, PCA. Independent component analysis. Singular value decomposition. Not. You've heard that one. Yeah, singular value decomposition. Non-negative matrix factorization. Complex matrix factorization? Anything right there? Nope. Guess what? You can still use them without knowing what they are, and they will reduce the dimensions for you. And we will give you a toolkit so that you can use them and be dangerous. It sounds like MATLAB stuff? It sounds like mathematics stuff. Did you guys say the same thing? Yeah. Have you guys ever heard of sparse coding?
Like coding of a vector coding?
Yeah.
Yes. Sparse tree coding.
Yeah. You can come up with a dictionary of examples that say each of them are 100-dimensional, right? And you have to go through and pick out 3 or 4 that best represent this unknown signal that came along. So you could use something like sparse coding. I didn't mean to go through this in this much detail. You could also use forward feature selection, where it's like, okay, I've got 100 features, I'm going to choose 5. And we'll see how that goes. And there's ways to go about selecting those features. You could pre-process the training data. This helps a lot by scaling and normalizing each of the dimensions that you have, so that they're, let's say they have 0 mean and a variance of 1. Why? Why would that help? Let's say I have new and k-nearest neighbors. Why would it help to scale and normalize each of the features that I have? Yeah, each feature is weighted equally in that. All right, fair enough. You could decorrelate the features, something called Wykening. You could make the features binary. You could just threshold them, right? So let's say we've got our iris data set. And we'd say, okay, anything above 1.5 is going to have a value of 1. Anything below that will have a value of 0. We just make our features binary. And that actually helps in a lot of different ways, right? In some way, we quantize this continuous value. So if you want to know anything about those, take a stats class. That's the last time you'll see it in this class. Okay, moving on. Now you know keywords, okay? And that is 60% of the battle in machine learning, is knowing what the keywords are. Hopefully you have a vague idea about these concepts that's going to help you with the intuition in using machine learning. It's going to impress some interviewer that you might have in the future. It's going to allow you to use toolkits without completely knowing the math behind them. And why is that important? Because that's what we're going to do. And no one knows the math behind all of these toolkits in a complete way. No one.
That fact.
That is a fact. Well, one person does, the person that implemented your entire toolkit. But usually this is a group of people. Okay? Unless you go down and implement these machine learning algorithms, you don't appreciate or understand all of the little nuances. But you still have an intuition about it. You can still use them. Right? Okay. So let's talk about Scikitlearn. It builds upon NumPy, SciPy, and ApplePy. It's essentially matrix math in Python, and SciPy is something that's used for math in scientific applications, right? These are toolkits that were built for Python to be used in this way. Essentially, what it is you classify a label based upon the features that we have. In Scikit-learn, there's a lot of different machine learning algorithms that you get to choose from, and they all work in almost exactly the same way, so that you can just take one word out, put another keyword in, and all of a sudden you're using something different. They do things like automatic data transformation and scaling, right? So I was like, maybe you need to input maybe you need to scale your input data. The command for that is data.scale. Done. It has a lot of text feature extraction, right? So we talked about TF-IDF really, really briefly last time. That's implemented. You can just give it text or point it to different files, and we'll put together all of those features for you. And everything that I'm teaching you now applies to big data as well, because essentially there are things that you can do with this toolkit for memory mapping onto the hard drive, so that if all of your data doesn't fit into memory, you can still use the toolkit. Or if you want to parallelize all of the different processes, you can do that with IronPython. So let's say you buy a little EC2 instance, you go up on Amazon, and you can train this whole thing up as long as you pay for the resources. Okay? Happiness? Good? That's Scikit-learn. All right, good. So next time we'll, no, I'm just kidding. Okay, so NumPy and SciPy. Numeric operations in Python. We're going to use it for creating feature vectors. That's all we're going to use NumPy for. But it's much more than that. So let's look at some code. If I want to use NumPy, the first thing I'm going to do, well, how would I get NumPy? How would I get this toolkit for Python? Import it? But you said download it.
Don't really have it downloaded if we are using Mac system.
Oh, NumPy might be included. It might be included on a Mac. It might already be there. If it's not, sudo port install NumPy. If you're on the Mac, or pip install NumPy if you're on a Windows machine. Yeah? Or Homebrew. Don't use Homebrew. I like Homebrew for a lot of things, but it breaks for OpenCV, and that's why I didn't like it. Anyway. Okay, so we're going to import NumPy as np. All right. So now I'm going to say a equals an np.array of 3, 4, 5, 5. If I look at the shape of a, it is 4 by... What is that? It's supposed to be a vector. It's 4 by nothing. This is one of the things I don't like about NumPy, which is why I've been showing to you right off the bat. You could also do something like this, where you say, hey, NumPy is equal to np.array 3455 dot reshape 1 by 4. Now if I look at a, there it is. If I look at a.shape, it's 1 by 4.
Why didn't they include the default implementation?
I don't know. I'm sure there's a really good reason for it. I've never found it. I've never looked for it. I'm sure it's there. Anyway, this is something you might have to deal with when you're looking at your data. Okay, so let's say we've got now a value of b. I'll do an np.array. And now this is another array of length 4, 6, 6, 7, 8. And it's got a shape of again, 1 by 4, because I called the reshape command on. All right? So it's 1 row by 4 columns, right? Okay, so if I were to call, okay, c equals numpy.rowstack right here, and then I give it a tuple, right? You can see this is a tuple of a, b, right there. What is it going to do? It's going to stack the rows on top of each other and make a matrix. Bam. Just like that. Look, it's a matrix. That's wonderful. What if I do column stack? Same thing, but make a longer vector. Awesome. We are now experts at NumPy. Okay. Actually, let's do one more thing. Okay, so if I were to access C at the 0, 3, what am I going to get? 5. Everybody see that? I'm going to get 5. Excellent. If I were to access C at the colon 3, what am I going to get? I'm going to get 5, 8. So give me back all rows in the third column. Right? 5, 8. 0, 1, 2, 3.
It looks like MATLAB syntax that started at 1.
It looks like MATLAB syntax, except it is properly 0 indexed. I like MATLAB. I used MATLAB in my dissertation. All right? I used MATLAB enough that now I'm using Python. So if I were to say, okay, C at the 1, comma, colon, what would I get? Based on what just happened back there.
6, 6, 7, 8.
Look at you guys. Got this thing going. Yes. Now, if I were to say I equals 0, 3, wait, do you not get it? Or you got it?
No, I got it. Just slightly dyslexic.
Ah, fair enough, fair enough. Your computers, are you messing up the 0 indexing of this?
No.
Okay, good.
I'm just messing up on how it reads the numbers off the board.
Fair enough. That's good. Okay, so if I were to say I equals 0, 3, and then I were to do this, okay, give me C at the 0, I. Oh, it works. What does it give me?
Something.
It should give you a matrix dimensions do not match error. I'm confused.
Nope. What it's going to do is it's going to say, okay, give me the 0th row, and then in that 0th row, give me the 0th and the 3rd number, 3 and 5. Right? So I is equal to 0, 3. So I'm going to say C at the 0. Okay, so give me C at the 0. So I'm talking about this row. And 0 and 3. Give me 3 and 5.
So you could have done like 0, comma 2, comma 3.
Nope.
No, you can only do 2.
I can, well, no, I could have done, okay, give me 0 and then given it a tuple for the other things in the column that I wanted. Do you know what I mean? Because well, I could have also given it a list. I is a list of numbers, 0 and 3, right? So.
That's what I'm saying. So you could make I 0, comma 2, comma 3.
Oh, yes. Yeah, you could. You could make it 3 numbers. And then it would give you 3, 5, 5.
Okay.
Right? Oh, I messed that up. This one. This one. Okay. So now, if I were to say max is equal to C dot max, what do you think I get? 8. Bam. Look at that. If I were to say max equals C dot max on axis 0,
Does it take just the norm or?
what it does is it says axis 0. Axis 0 means along this. So take the maximum among these two, these two, these two, these two.
Okay. I thought
And
it
it
was
just
like
happened to
finding
be
the
the
max
bottom
vector.
one and everything.
Yeah, I messed that
So
up. This I should have switched some things around.
But it would mix and match if it worked out that way.
Absolutely. Take the max along each column.
Could you how would you, is there an easy way to specify how to find the biggest magnitude along that axis? Or would you have to do separate, find the magnitudes and then find the max?
You mean like taking an absolute value?
Yeah.
Yeah, you can take an absolute value of the matrix and then dot, like max of absolute value of matrix. Like almost exactly like you would do in MATLAB.
Okay.
Yeah. Yeah. NumPy, SciPy, they're actually built to be really, really similar to MATLAB, except 0 indexed. And they support memory mapping, which MATLAB does, but these do it better. All right. You can also do things like numpy.linear spacing right here. So this, I want 30 values between 0 and 3, linearly spaced from one another. What does that do? That gives me 30 values between 0 and 3, linearly spaced between one another. Okay? Now, I can do, if you're familiar with MATLAB, sine of t equals np dot sine of t. And that gives me back the sine of t. Pretty cool. Wow. This is awesome. Is it? Okay. You don't have to agree with me. I could also do this. I could say the FFT of sine t is equal to np dot FFT of the sine of t. And it would give me the FFT of that array. Wow. Most of the things you can do in MATLAB, you can also do in NumPy, at least for matrix operations. Okay? We are going to be using NumPy for feature vectors. So that's all we're really going to talk about with NumPy. Right? I just wanted to give you kind of a flavor of how to index into those arrays. Okay, so let's say we make a vector of feature vectors. So this is the notation that we're going to use for Scikit-Learn. With Scikit-Learn, we need to give it feature vectors, right? And we need to tell it which of those feature vectors come from a different observation. You guys know what I say when I mean observation? Right? You have a feature vector of observations, and you have a label for that observation, right? Feature, label, that's one observation, right? So if I were to say features is equal to np.random, and I get a 10 by 5 matrix, this is what it's going to look like. I'm going to get 10 rows and 5 columns. Okay? Pretty cool. So I get this random. This right here at the very, very top, that is the 0th feature vector, the 0th observation. Here's the first observation. Go all the way down. Here's the 9th observation. Okay? So I've got 9 observations with 5 features in each feature vector. Right? That is the structure that Scikit-Learn expects it to have. Right? So each row is the observed feature vector. Each column is a separate feature. Any questions on this? If you don't get this, then you won't get the rest of the slide. So ask if you got a question. Good. All right. Here's Scikit-Learn. Here's the way that it works. Essentially, the workflow is, let's say when you're going to create a model, that's everything that you see with the blue arrows. And this is, you can find this image on scikitlearn.org. Let's say you have like some training text, documents, images, something. You can use Scikit-Learn to come up with the different feature vectors that you want. Or if you just have feature vectors, just cross that little part off right there. Maybe you've already got a vector that you want to import, right? So you take the labels, you take the feature vectors into your machine learning algorithm, right there, all of the different algorithms that we already talked about. And then that gives you a model. Now, whenever you have unknown data that comes up and you want to predict something about it, what you're going to do is you'll put it through the same kind of process that you did with your turning your training into feature vectors, or you'll just take the raw feature vector if you already have it. You'll put that into the predictive model and you'll get an expected label. Okay? The commands for doing all of this are these. So let's say your input is input. You can call x is equal to vector.fit transform your input, and it will turn it into feature vectors. If you've already got feature vectors, don't worry about it. Let's say you've got a classifier, and it's called CLF. You can call CLF.fit x and y. What do you think x is? Your feature vectors, all of them, concatenated into one matrix like we talked about. What is y? It's your labels. And how many labels do you have? One for each observation. Man, we are moving along. This is wicked. Okay? So now, when you want to predict something, you're going to save that vector variable right here where you fit the transform, right? Because now you're going to say vector.transform your input into features. You turn it into features. And now when you want to get the prediction, you call, hey, y new equals clf.predict x new. What is x new? It's some feature, it's your unknown feature vectors. Right? Maybe you've just got one that you're trying to, maybe you've got a bunch of them that you're trying to put together. Right? So you call the classifier that you already fit to, you already called clf.fit on that class. So now we're going to call clf.predict on x new. And y is going to be predicted labels. Hopefully they're the right ones. Question?
Maybe this is a stupid question. Are there any machine learning algorithms that don't work with finite labels? Does that make sense? So they have
With a finite number of labels?
Yeah. So it's like if there's an infinite number of labels, but you train it with a finite amount. So like continuous spectrum labels.
Well, yes. The one thing you can do is regression, right? But that's a little bit different because it's a continuous value, right? It's an infinite number of values. It's continuous. The other thing that you can do is have an unknown class, right? So if you were to use something like expectation maximization, you can essentially fit a bunch of data, or it also has a class where it's unknown. Usually, you need to know how many classes you have.
So it'd be better to take those infinite values and then group them and say there's a range of classes and we're going to call this one class.
Yeah, I mean, if you don't have a label for something, it's never going to be able to predict it, right? So if you've never seen it before, it will never predict it, no matter what machine learning algorithm you have. Okay, so in Scikit-Learn, there's a lot of data sets that are already included, right? So how do I install Scikit-Learn? sudo port install scikit-learn. Done. Okay, now when I want to import it, I say, okay, from sklearn import datasets. And then I have access to this. I could say datasets.load iris. And it's going to load up the iris dataset that we talked about before. Right? So the feature data is going to be under the iris.data. The target is my labels. That's under iris.target. All right? So iris.data looks like this. There's a bunch of different observations. There's 150 observations, and each of them is 4 features long. Right? Good. The target, there's 150 targets, and they're all either Certosa, Versicolor, or Virginica for the different iris values. That is a vector. Yes. It's just printed really poorly. Yeah. Okay. So maybe I want to do some pre-processing on that feature vector. I could say, okay, from sklearn import pre-processing, and I could say feature data is equal to preprocessing.scale feature data. And it will make it 0 mean and between 0 and 1. And I'm done. Okay? So let's get a classifier and train it. From sklearn import tree, and now I can say clf equals tree.decision tree classifier. What that told scikit-learn to do was get a handle to a tree classifier. Okay? Now what would I do? Let's say I've got my iris data set. If I want to train it. I could say clf.fit, and I would give it the data and the labels, x and y, just like we talked about. And what it's going to return is a trained decision tree. And now if I want to get a prediction, I could say predicted equals clf.predict, and then I could use this iris data again, right? And it's going to give me a prediction for every single row inside of that matrix, right? So now I can say from sklearn.metrics, I'm going to import an accuracy score, right? And I want to say, okay, my accuracy score is, let's look, this is the targets that I want, and these are the predicted values, and I get back 1. What does that mean?
It means you have a perfect score because you compared exactly what you trained it with as the prediction set.
Yes, I just predicted all of the labels from my training, right? This is called resubstitution. All right, it's a fancy name for, hey, you just ran something, predicted something on something you trained it with. Resubstitution. Okay? Really, we should be using cross-validation sets. And you can use cross-validation sets in scikit-learn. So.
You mentioned 90 training, 10 validation. Is that the common ratio that's used?
Yes. Most commonly, you'll see people use, if they only have like 9 examples of something, which happens, they'll use leave one out cross-validation.
Oh.
You know what I mean? So like they'll train it up on 8 examples, test it on 1. Pick a new 8, test it on the other one. Right? If they have more than that, you'll use tenfold cross-validation. Right? And the reason that they use tenfold cross-validation is because empirically it just has the lowest bias without being overly, it takes a lot of time to train 10 different models, right? So if you were to do 20-fold cross-validation, it takes even more time.
So 50-50 would be bad.
50-50?
Yeah. Half your data used to train, half your data used to validate.
That would be, yeah, I mean, if you chose your folds really, really well, right? Like this was an example of your data set, and here's another really good example, just like statistically good sampling of your data set, then that's okay. But if you don't really know that, which you probably don't right off the bat, use tenfold cross-validation. Empirically, it'll give you the lowest bias. There's a lot of math to support that, none of which anyone needs to know. Good? Okay, scikit-learn. Let's do a demo. Oh yeah, it's only 4:36. Let's do this. Okay, let's go over. Do I have something open? Is that? Oh wait. Hey, scikit-learn. Okay, I've got a bunch of different examples which I've actually already posted online. Or maybe I haven't, because I don't know if tutorial 20 was up. So let's do this one. Let's take a look. Okay, so with, oh, come on. Okay, so I've got a bunch of different imports, including things like cross-validation, support vector machine, tree, data sets, logistic regression, k-nearest neighbors, random forest classifier, Gaussian mixture models, and preprocessing, just in case you didn't want to throw a bunch of stuff in, right? So what am I doing right here? I'm loading up the iris data set right here, data and target. I'm go ahead and preprocess it. I'll scale it, right, like everything that we did. And then I'm going to create this vector right here, which is target times 0. That's going to be all of my predictions, just where I'm going to save them. Okay? I'm going to create a classifier, and it's an SVM dot support vector machine classifier, SVC. I could have also done a support vector regression, right? But I'm doing a classifier here. And I'm going to give it some setup parameters. I'm going to say, hey, use that Gaussian, the radial basis function, RBF, and give it, c equals 100, gamma equals 0.001. Okay? These are just numbers that normally you'd have to play with, right? Or you could do a grid search on them and find out what's the best for your data. So what I'm going to do here is I've got my target and my feature data, and I'm going to say that here's target. The number of folds that I want in my data set is 10, and I'm going to call cross-validation.stratified k-fold. What that means is just select randomly, but try to make sure that there's an equal number of classes in the fold and the test set, right? So don't choose all of one class and try and test on a class I've never seen before. Right. So now I'm just going to run this in a loop that says for train CV, test CV, inside CV, right there. Well, I'm going to call this right here, clf.fit, my feature data at the training cross-validation, and my target at the training cross-validation. Then I'm going to call clf.predict on my feature data at the testing part of my cross-validation, and I'm going to save it inside of this vector. Right there. Okay? And then I'm going to come up with an accuracy score from that. This is my target and my predictions. Okay? And let's run it. Terminal, change to desktop, Scikitlearn. Okay, we'll run Python 2.7. What's up? Nothing? Okay, good. Fair enough. Can't see it? Terminal. Preferences. Change. 24. So Python 2.7, this is called sklearn_iris.py. So if I run that, it's going to come up with a couple of things for me. My total accuracy is 96% on the iris data set. All of the setosa was classified correctly. You guys know what a confusion matrix is? Right here? You can kind of figure it out pretty easily, right? It is, here's the true label, and here's what I predicted down here, right? So if it was a 0 setosa and I predicted a setosa, I'm going to graph it right there, right? If this was a setosa and I predicted versicolor or virginica, it would be right here. You can see there's a couple of different confusions between versicolor and virginica down at the bottom right. But for the most part, this is a really good classifier. It's a really good classifier because everything's right along that diagonal, which is where I want it to be. That means it was a 0, I predicted a 0. It was a 1, I predicted a 1. It was a 2, I predicted a 2. Excellent. Right? And I used Matplotlib to get all of that in there. Okay, wonderful. This is great. Moving on. What else do we got? You guys wanted more examples? You do? You don't? No? We're done? I don't know what's going on. All right, let's look at tutorial 1. Right? This one I'm going to load this thing up called the digits data set. right? And then I'm not going to do any machine learning. What I'm going to do is I'm going to print 20 of those digits to the screen. All right, let's do that. Oops. Python 2.7 Scikitlearn underscore tutorial 1. All right, so I'm just randomly printing out these digits. There's number 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, whoops, 1, 3, 4, 5, 6, 7, 8. They're just really, really low resolution pictures of handwritten digits, okay, that people have gone through and someone used a scanner and you're trying to predict whether or not, what number these values are. Okay, so let's predict. Let's do something with it. Tutorial 2. All right, so with this one, it's essentially all of the same code that I just showed you, except I'm going to give it a test set size of 100, right? And essentially what I'm going to do here is I'm going to create a support vector machine right here, and I'm going to train it up on all of the digits except those in my test set by doing this. And then I'm going to, I'm going to train it on everything except my test set, which is what this line of code does. And then on the very bottom down here, it says predicted equals predict digits.data from 0 to the very first 100 examples, right? So I think there's something like 3,000 examples, right? So I'm going to train up a support vector machine. What are my features? Does anybody know? Yeah. What? The pixel values. Yeah. Yeah. Each of these handwritten digits is like an 8x8 block. I'm just going to take all of those pixels and string them together into a 64-dimensional feature vector, right? 8 times 8, 64. 64 dimensions. I'm going to say that was a 1, or that was a 2, 3, 4, 5. And the numbers 0 through 9. Right? So now when I have those unknown, I'm just going to throw it in there and see if it can predict it. Okay? Does that seem really stupid?
No.
It doesn't? It's not, as it turns out. Why? Because I'm using a support vector machine, and it can handle that. Doesn't really care what I give it. All right? But let's see what it comes up with. Let's run this. And what happens down here is anytime I get an incorrect digit out of the 100 digits, I'm going to display it right here. That's what this code does. So let's just run that. And this is tutorial 2, I think. There. Ah, no, oh, come back. So prediction was 5. Actually, that was a 9. Prediction 7. That was actually a 9. I predicted a 1. That was actually a 2. 96 out of 100 I got correct. The other 4 I messed up on. That didn't take very long to train, and I trained it on something like 1,000 examples. What's up? What's going on over there? All right.
Nothing. Literally nothing.
Okay.
Kevin just can't type, is what happened.
Yeah, this looks good. Questions? Huh? I used 100 tests.
Oh, those.
Yeah, the remainder I used was something like 2,000 or something. Good? All right. Now what? 4 minutes left of class. Let's go on to the next subject.
Yeah,
Another example? One more example. Oh, you guys are getting good at this. Number 3. I don't even remember what number 3 was now. Let me look. Oh, this reads in example data from a CSV file. And that CSV file is right here, exampledata.csv. This is Numbers. This is a lot of numbers. I think this is my wine data set, where it's essentially like a wine rating that happens here is 1, 2, and 3. And then it has different features, including like the alcohol content of the wine. This is like something from, I think so, but I can't remember. I don't remember where this came from. No, the output doesn't have pictures. Then never mind. Okay. This is good. This is good. So essentially we've got 4 minutes left of class. Should I run the iOS example? We should run the iOS example. I'm just going to go into what this iOS example is. So do you guys remember the HTTP example that we did a week ago? Yes, it was there. Awesome. We were sending up these JSON things. The web server was like, sweet, we got it. I'm going to put it in MongoDB. Yeah? All right. Now that web server is going to be, let's see if I can, where do I go? Python. Tornado. It is going to be a machine. Scikitlearn handlers. Here we go. Open with Xcode, whatever. Wow, that's easier to see. Well, I've got this thing now. It's called my upload data point handler. What do you think my upload data point handler does? And saves them into MongoDB. All right?
Why didn't you make it upload and save them?
That would have been a better name, right? I'm using, oh no, this is still Python convention. I'm still good. Okay. So I was looking at my capitalization techniques, right? Essentially what I've done here is I go into my JSON loads and I look into the body of my request. By the way, this is a post request, so I'm looking in the body. And I grab the values from feature, right? So this is a dictionary entry. So I've got some feature, which is values. And then I've got something here which is called DSID. What do you think that is? If you were going to upload data to a web server, would you want to flag it in some way? A data source identifier. Bam. So if you're running your iOS app, you're going to say, hey, give me a data source identifier. And it's going to be like, sweet, your data source identifier is 0x0a. You're like, okay. So now when I've got some data, I'm going to upload that, and I'm going to tell it to save it with the ID 0x0a. So that way, whenever I want to train a model, I'm going to say train a model on the data set corresponding to 0x0a. And it's going to train a model, and it's going to send predictions back down to me using that model. Is that okay? All of that code is written for you, and it's posted online, or will be posted online. Okay?
Enforced by you or by Scikit-Learn?
Both, I guess. I use Scikit-Learn to do all the machine learning, but I wrote that code to do it. Don't release that code, by the way. If you guys want to use it, that's fine. And this is actually, it's a pretty robust thing. I've used it for stuff that I've used in industry. It's pretty cool.
So is there a way to, if you make a decision tree, is there a way to save it somehow in a database, or do you have to?
Yeah, so the code that I give you, you can say another URL that you can upload to, say, hey, train model for 0x0a. It will train the model, binarize it, it's pickling, that's what it's called in Python, save it inside of a database, and then whenever you want to predict something from that, you say, hey, predict it from this model, and it'll go load it up, do a prediction, spit it back out for you. Okay? And we'll go over all of that next time, or maybe in lab if you guys want to get started. Because you could probably do the entire assignment this lab and just free yourself up next week. What?
You say that.
Well, you should probably start anyway. Okay? It's just me trying to get you guys to start the project this week and not do it next week.
Right.